Hi, hello. Welcome to the Exam 3 review. So, a couple things to keep an eye out for. One is the office hours schedule for this week. So immediately after this, I'll have a couple hours of office hours after a little break. And then Chris has a couple hours tomorrow. Skylar has some Wednesday. And then Sabrina has one as well on Tuesday. And then the exam is Thursday during our normal class time. So, today we're going to be mostly doing some practice to try to help get ready for the exam. I think if you've gone to the first two exam reviews, we've split them up with the TAs, so we've each taken one. Mine's going to be probably closer to Chris's because both of us are using this notes document that a previous head TF named Brandon made. So all credit to him for these questions, which I think are quite good and quite representative. He was with 27 for I don't know, a decade or something. He was head TA of the class back when I took it in 2016 or 2017. So he knows this very well, and I think the problems are representative of exam level problems for this content. So we'll start off with the Q&A. Most of these you probably know now that it's the third exam in the class. What content's tested? So the first 9 lectures, but really 7 through 9 is what's hit heavier. So let's think about kind of what happened in lectures 7 through 9. So we had electron sinks. With this, we had TPP and we had PLP. We had aldolases. We had fatty acid synthesis. I think those are kind of the big cofactors and domains that we covered. So that's going to be what most of our practice is on today. What's the format of the exam? How similar is it to the practice exams? Identical in format to the practice exams. The practice exams are your best representation of what the actual exam is going to look like. I believe both these practice exams were actual exams in the past, so they should be quite representative. And what's the best way to prepare? Well, certainly the practice exams is kind of the biggest. But reviewing P-sets, section, lecture notes, the general kind of studying. So hopefully today we'll do some practice. I'll put it all together. But because of how important the practice exams are and how kind of representative they are of the real exam, what I decided to do was just a little analysis of the two practice exams. And I think looking at this, it's not going to be spoiler alerts if you haven't taken the practice exams and still want to take them kind of blind. I don't think that this is going to ruin anything. But I just tried to go through each of the questions and subparts of the questions and be okay, which of them are mechanism questions, which are theory questions. Mechanism, you're doing curved arrows. Theory, you're doing anything else. You're drawing a product, you're writing a sentence, an explanation, something like that. And exam 3A versus 3B, they have different numbers of questions, sure, but we have a lot of things in common. So a couple of trends here. Both of them have 2 PLP mechanisms on them. So you're definitely going to see some sort of PLP mechanism. And one of them, each time, is a PLP decarboxylation. So, just because we've seen that so many times, it was on the homework 2 or 3 times, I think, for the PLP lecture, decarboxylations. I would try to have her locked and loaded and ready to go. And then also remember we had that weird PMP kind of shunt that we could do with PLP for transaminations. So you have one of these in practice exam 3B. We're going to do one of these today. And then each one had an aldolase mechanism. So a straight up aldolase, making sure we know, bringing in our lysine active site, and making our iminium to do all of that. Each of them had a TPP mechanism, and in one of them it was a decarboxylation, and the other one it was this complicated one. And the 2 hardest mechanisms on the practice exams, in my personal opinion, I have made these dark colors down here. For one of them, the hard one was a TPP mechanism, where you're doing a simple TPP thing, but complicated other stuff. And over here, similarly, you're doing a simple PLP thing, but complicated other stuff. And so it's assuming for these kind of harder reactions that you have enough fluency with the cofactors that we can ask you some trickier chemistry. And we'll talk about doing some analysis of these to kind of break down what's going on and get a make and break list of bonds that you need to form. Each exam is asking you about the MO requirements of an electron sink moment. So typically that's TPP or it's an aldolase, because remember carbonyls can be used as an electron sink. So expect that to pop up in your exam. Like you are going to have to do an MO argument. Each of them covers FAS with kind of mechanism and theory of doing some mechanism of substep, and then doing some theoretical work, either predicting products or labeling or talking about inhibitors, things like that. On practice exam 3A, it greatly expanded the FAS stuff. So FAS had a lot of different parts to it. And then for 3B, FAS was much shorter. Then the last two are a little kind of idiosyncratic. Like, I don't think that we hit it as hard, but this E1CB mechanism. So we saw this with one of the inhibitors, with like getting a fluorine off of a molecule. And then we also see this mechanism as part of the aldol reaction. We'll review it kind of explicitly to talk through that. But it was a mechanism that I saw both over here in this like PLP fluorination question, which is similar to a lot of homework ones that you've seen. And it popped up in exam 3B. So I would kind of keep a hard eye out for this. And again, we'll talk through some of that today. The last big one, and this is kind of where we're going to start with our review today, are kind of analysis pages. So my favorite way to describe this skill within chemistry is like reading the room chemically. Of like, we drop you into a reaction and we want you to be like, oh, okay, this is a reaction that requires a PLP cofactor, or this requires TPT, or this is doing an aldolase, and okay, we've made one of the products out, but then there's another product missing that we want you to supply. That kind of analysis, you have a full page of it on both exams, and then you have kind of a partial question of it as well. So I think that that's going to be a significant part of your exam. So that's kind of what we're going to start with today. And the general game plan is we are going to go through all of these problems. These are the kind of analysis questions. We're going to be just figuring out what's going on. Then we have a bunch of mechanisms. And after we do this, if we still have time, then what we might do is jump into some of the practice exam questions. And we can even try to do the practice exam questions that I think are like hardest, or we could just go through or into the practice exam questions that y'all want to do. So I might be like, vote in the chat, blah, blah, blah. And we'll kind of take it from there. But we'll see how much time that we have after we go through a good chunk of this. So that's kind of overview game plan for today. Are there any like logistical questions for what is going on and what this kind of review will be, or things about the test? I will also say I have not seen the test yet, so I can't give sneaky hints. We had a separation between church and state of that. So
I have a question.
yeah.
How do you suggest best preparing for like mechanisms that aren't maybe like elaborate on the chemistry in some way that is like not consistent with our PSET and like exam questions? Like, is there a way to go about understanding, I guess, the theory behind the mechanism that would be helpful?
Yeah, so I think that there are kind of two parts to it. One part is your analysis of a question when you get into it. And so it's going to be mapping carbons onto each other, numbering them. And we are going to do a lot of that analysis practice together here, because we're going to be doing some mechanisms that have some slightly weird things. The other part that you can do to best prepare for those is be locked and loaded on exactly the mechanisms that are the typical textbook ones that you've seen before, so that you can better recognize when we're doing like a little theme and variation on the tried and true what has been in lecture. We are never going to throw chemistry at you that we don't think that you can figure out. But ultimately, we are not trying to test you on how well can you reproduce what's in a textbook. We're trying to test y'all on like how well have you learned how molecules react. And so, like, part of how these questions and these tests are designed is to put you in situations that are slightly uncomfortable, where you're going to have to kind of like improvise and think through that on your own. But again, that's something that I think that as we do some practice, we will talk through some of those strategies more explicitly. But I know that is a little anxiety producing, so sorry about that.
Thank you.
Cool. Yeah. Chris.
Well, and I'm not sure. I don't know if I can see it on my. Are you recording right now?
I am. So
Okay, cool.
I don't record with the Zoom platform just because I feel like it makes kind of crappy recordings. So I have like OBS set up.
No, totally. But I just wanted to. I didn't see anything that was like currently recording, and I was like, I hope this is being okay.
And it's also a thing that like I don't think that y'all are being recorded, so that's why Zoom did not tell y'all. I'm just recording like my screen and my mic.
Okay, cool. Thank you.
Totally. Cool. Any other questions before we jump into some analysis and kind of the reading the room skills? Okay. Let's try it out. So, for these questions, we are going to identify which cofactor, if any, is required for each transformation. Co-products are not shown for parts B through G. Draw the structures of any co-products not pictured. So, let's take this one step at a time. Step 1 here, we are looking for a spot the difference game of what has changed. And the thing that I am seeing is over here we have a carboxylate, and then we've added a phosphate group. So, if we are adding a phosphate group, what cofactor do you immediately go to? Like, where have we seen something that can add a phosphate? Feel free to chat or unmute. A in the chat. We already have an answer. ATP, something that has phosphates that move. So, we are making an acyl phosphate out of our carboxylate. And why do we do this? Like, what's the purpose of adding a phosphate onto something? Well, it now is a good leaving group. So, I have a feeling that we're probably going to do something with this now that we've activated it by adding a phosphate group. So that's the first one. Step 2 here, we're looking at this, and where is the change? Well, I see it here. This is now an aldehyde. So here I'm saying, okay, we are oxidation level 3, and now at an aldehyde over here, we're at oxidation level 2. So we've done a reduction. So throw out a cofactor we might use for this. Yeah, so NAD parentheses pH, whichever one. ADBH. So we need something that already has the H on it, so we're going to have it with the H rather than without. And then one thing I'm seeing from the chat, Kamala had a great point here. We technically do have another coproduct here where we're going to spit out an ADP after the first step because we added on a phosphate, and so we are also going to be making an ADP. That wasn't even in the answer key, so nice catch. So with this, we see the phosphate group get kicked off, and then we are at our aldehyde here. Okay, so now that we've done our reduction, this molecule is going to go and do 2 different pathways. So let's focus on the pathway down with step 3 first. So I'm seeing a whole other big molecule come in and leave. And the things that I'm seeing on here are this amine got turned into a carbonyl. And then in this starting material, this amine, that stayed there. This carbonyl got turned into an amine down here. So when we are swapping an amine with a carbonyl, this is a reaction that's called a transamination. And transaminations are done with the PLP cofactor. And this is going to be that long version of PLP mechanisms that goes through a PMP intermediate. That's when we kind of break off the iminium from the rest of the ring. And that's what allows us to remove the nitrogen from one molecule and put it on another. And so very specifically, we are taking this nitrogen that was on this molecule over here, and we are installing that nitrogen over here on the product. So on this original molecule up here. So that is going to be our PLP. And then we are looking at this step 4 kind of shunt over here. So what is the change between this? Well, woof. I'm seeing a carboxylate, so I'm going to go ahead and start to try to label some things. So I'm going to label this carboxylate with a star. And then I had 1, 2, 3, 4 carbons after the carboxylate. The numbers don't matter, just as long as you have a system. So now I'm thinking 1, 2, 3, 4. So what I'm seeing is this aldehyde over here is now iminium over here. So I think that this is just imine formation. And so do we need a cofactor for imine formation? Nah. So this is imine formation. And we have no cofactor. And then finally, over here, going from an iminium, I look at the product now, and the product just has a plain Jane amine. So specifically, this carbon here has gone from an oxidation level of 2 to an oxidation level of 1. That carbon at the corner is only attached to one electronegative thing instead of 2 bonds to it. So we're doing another reduction. And with that, we are going to use the same NAD parentheses PH. And so maybe to help us see that as well, I'll go ahead and put that on this original one, we had 1 hydrogen, and then over here we had 2 hydrogens. So we added a hydrogen. When we do that, remember, so when we are loading in NADPH, then we have to offload an NADP+. And then PLP is reformed at the end of it, so we don't have anything to do with that, and then there was nothing there. So that's our first kind of example scheme. Any questions on this before we do some kind of shorter ones, one-off ones? Cool. Okay, so it said in A, this whole big example, they have all the cofactors and coproducts. We just need to supply cofactors and they have all the coproducts, but in B through G, we have to supply any coproducts. So that's one thing that we're going to be looking at. We might have something else that is formed. So when I'm starting to look at this, the first thing that I'm kind of doing is I'm counting carbons, 1, and then 2, I'm looking for key structural features. So carbons, I'm seeing 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbons on this side. And the 8 carbons are as a 3 and a 5 carbon. And our product over here has 1, 2, 3, 4, 5, 6, 7 carbons. So we have removed 1 carbon. We need a 1 carbon thing over here. And what's our most likely 1 carbon thing that we remove? Well, probably a CO2. That's the most common thing that we've seen removed. And let's see if we can start to map those on and make those make sense. So now, with this, the most kind of like standout structural feature that I'm seeing in this molecule is our little fishtail, our little isopropyl here. I feel pretty darn sure that those two are the same. Just because, like, we aren't really making any other, like, methyls added onto things really easily. Like, we might make carbon-carbon bonds in the middle of a chain, but this kind of terminal feature with two methyls, that seems harder to make. So if we do that, then I'm thinking, okay, this star carbon, square carbon maybe, star carbon, square carbon. And then I'm saying, okay, well, the other carbons on here, we have a methyl, and this methyl is on the end, it's terminal, and then we have a blue star carbonyl. I have a feeling that that's this methyl on the end and blue star carbonyl there. So that would make this carboxylate probably the CO2. And that makes sense because the carboxylate's the only thing that we have here that's at oxidation level 3, and CO2 is at oxidation level 4, so she has the shortest distance to get there. The other thing that we might notice about our left starting material over here is this starting material is called an alpha keto acid. So it's like we have a carboxylic acid or carboxylate here, and at the alpha position to it, we have a ketone, alpha keto acid. Now, alpha keto acids were the prime example that we used to introduce an opportunity for TPP to act as an electron sink. Because beta carbonyls, those have like a natural built-in electron sink. That's the Claisen decarboxylation stuff that you've seen. But at the alpha position, we can't fold this in and then push these electrons into the carbonyl that's already there. So what we need to do is we need to use our TPP cofactor, and we need to install an electron sink at this position so that we can do a decarboxylation of that alpha away from it. So one thing to remember is TPP, what is it looking for in order to install? Well, it is looking for a ketone or an aldehyde. Those are the positions where a TPP can come along and plug in. And we see, hypothetically, we have 3 of these that we could go and plug in at, but only one of them is next to the bond that we are breaking. So we know that TPP is going to come in at this position. Cool. So with that, the general game plan for this seems to be we'll install TPP, we'll decarboxylate it, and then remember when we load an electron sink, it creates a nucleophile that can go and attack something, and then it seems like it's going to attack this square carbon over here as the electrophile. So I always like to see, like when I'm doing electron sink, what's our leaving group? Well, here it's the CO2. And what is the electrophile we attack? It is this carbonyl. And we're not doing the full mechanism of it, but again, I'm just trying to see what is all the analysis and helpful information that we can get out of just looking at a line reaction in order to best prepare ourselves for success and for weirder things on a mechanism. Okay, up next with part C. So I'm going to start off counting carbons again. So I have 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5 carbons. And in my product, I have 1, 2, 3, 4, 5, 6, 7 carbons. So I need another product that has 2 carbons to make them equal on each side to 9 carbons total. Now, with this, I'm trying to think about like key structural features that are going to be the same on both. And one of the things that's standing out to me this time is a carboxylate. So carboxylates that we easily could remove as a CO2, but we don't have 1 carbon leaving, so I don't think it's that. And we don't have any other carbons in the starting material that are oxidation level 3. So my guess, my money, is that that carboxylate in the starting material is this carboxylate in the product. So if we do that, then I feel pretty secure that the next carbonyl is this. And then I have to start being wary. Like, I don't know at what point this molecule ends and then the next molecule starts. So let me look at the other molecule and see if I can like find any hints there. Well, one thing, that it doesn't look too exciting. Like, it's not going to draw your eye. But this ethyl, do you think that that could maybe be that ethyl on the end? Because alkanes are pretty darn boring. Like, unless we have an oxygen on it or a carbonyl or something, like, we probably aren't doing a reaction with it, right? And so I feel pretty confident that this ethyl in the end, in the 4-carbon chunk, is this ethyl in the product, which would make this kind of blue star. And then I have to ask myself, which is more likely? Is it more likely that we cut off this 1-carbon chunk, and then this is a different carbon than the one that's over here? No, that doesn't make sense to me. Like, we would have to cut off a 2-carbon chunk to get this 2-carbon product. And so I'm thinking that this, I'm going to call blue square, is probably this one that's the OH over here. So now I just have like a couple of more carbons to account for, right? Like, I only have one more in this that I have to count for in the product. And I'm pretty willing to say that if we go one more out over here, that carbon, the green square, is probably this green square in the product. Just because it would be weird to be adding a new carbon in there. Like, the green star is most likely or most easily connected to the green square in the starting material, so it's probably still going to be connected in the product. And to check that intuition, if now I cut after that piece, that makes a 2-carbon chunk, doesn't it? So I'm thinking that this is going to leave somehow. We're going to have a methyl and then something else. But at this point, we should probably try to see what cofactor we're using. So if we did a TPP, we look for a ketone and aldehyde, and we cut between the carbonyl and the alpha position. So here we have our carbonyl that we install at, and the alpha positions, and we cut in between that. So that makes sense. Well, here, if we tried to TPP install at this carbonyl, that would be cutting at this position. That's not what we want, right? So let's think about our other ways of breaking bonds. And the thing that's kind of jumping out to me right now is here we have this compound functional group that from like the end of Chem 17 we were on the lookout for. And because of the reactions covered in these last 3 lectures, one that you should be looking out for, this is an aldol. In other words, it's a beta hydroxy to a carbonyl. And anytime we are cutting between the alpha and beta positions of an aldol, we are likely doing the retroaldol reaction, which means that we are doing an aldolase. So in aldolase, we are cutting between the alpha and beta position of an aldol. And in a typical aldolase, we have, or within the aldolase camp, I should maybe say, we have 2 flavors. If we only cut, then we are doing a classic aldolase. If we cut and attack a new thing, we are doing a trans aldolase. So a classic aldolase is just going to be a retroaldol. A trans aldolase is a retroaldol plus a new aldol reaction. So, with all of this, again, this is terminology that you don't necessarily have to know, but I think it can be helpful to be on the lookout for and to kind of classify this in our heads. Because I know that there was a tricky like homework question that was asking you to determine between TPP and aldolases. And one of the distinctions that we had is aldolases are just cutting, whereas TPP, you can cut something and attack something. There's a flavor of aldolase where you can cut something and attack something new, and it's this trans aldolase flavor. So, for trans aldolase, what cofactors do we need? None. So, with this, all we need is something in the active site. We need a lysine, because we know that this is going to go through amine intermediates. So that being said, when we do our retroaldol, we are going to disconnect here. And this side was originally the enolate that attacked, and the other side is going to be the carbonyl that was attacked in an aldol reaction. So our other product, we're going to oxidize it up to a carbonyl here, and then it has a hydrogen on it. So it's just acetaldehyde. I know that this is a harder example. What questions do you all have on this?
Hey, Colton, could you just repeat that last part again? Sorry.
Yeah, no, totally. So, just generally speaking, in a retroaldol reaction, the disconnection that we do is we are cutting between the alpha and beta position, and the alpha side was an enolate of some sort. It was the nucleophile that attacked because enolate have carbon nucleophiles at the alpha position. And the beta position was the electrophile of an aldol. So it's going to be a carbonyl. And because this already has a hydrogen on it, it's an aldehyde. It just, the hydrogen we weren't writing out. And so that's how we get to this as the other product for the reaction. Is that more clear, or is that, okay, cool. And with that, the kind of general game plan that we would do is, one, we would have our imine formation at the green star carbon. Two, we would do the retroaldol and kick off the 2-carbon product. Then three, when we do that, are going to form kind of an enamine nucleophile, because remember, we're going to be connected to our lysine. And this enamine nucleophile then is going to go and attack something else. Well, we know that this green square is attached to the blue square in the product. So we know that this is going to be our enamine nucleophile site, and it's going to connect to this as the electrophile that we attack. So we are going to do a forward aldol reaction with the 4-carbon chunk. And then after we do that, we are going to remove the imine. We're going to do the imine hydrolysis. Also, to be clear, I'm writing a lot of stuff to be like, how much information can we get out of just this line reaction? But the thing that you would be graded on for this is none, clocking that this is somewhere in the aldolase family, and what is this product. So this is all just helpful kind of analysis for like, what is all that we can extract before jumping into a page-long mechanism. Okay, D, slightly shorter. So in D, I'm looking at starting materials and product, and this one feels a little bit easier. This one, it feels like we just removed a CO2, right? 1, 2, 3, 4, 5 carbons over here. Here we have 4 carbons, so we need a 1-carbon chunk. So we have CO2 as a gas. So we're doing a decarboxylation. And so anytime we're doing a decarboxylation, we can use either of our electron sinks. We can use TPP or PLP. But we have to look at what are our install sites that we have next door to the thing we're cutting. So here we have an amine as our install site. So what cofactor does that mean that we are going to use if we're installing an amine? Well, PLP. So PLP, just like for TPP, we said look for carbonyls, ketones, or aldehydes. For PLP, we are going to be looking for an amine, and we are going to cut between the amine and one carbon away. So that's exactly where we see this decarboxylation cut. And then I had a question, are the mechanisms for these going to be shared? So these problems, I don't think we actually have a mechanism answer key. And I'm not totally sure. Some of them might be showing up in some of these problems, but they might not be. Honestly, I think these would be great practice. And so one thing that we can talk about once we get through the questions in this chunk is if we want to, we can just take some of these and do a full mechanism out of it together. And that can be extra practice that's not in the practice exams. So we can be thinking about, do we want to do that, or do we want to do some practice exam problems if we have extra time? But I will keep plowing away for now. So yeah, this was just a classic decarboxylation. Moving on to E. So interesting stuff. I mean, to me, the most distinctive feature is probably the phosphate group, because we probably didn't remove a phosphate group and add a different one. And so if we have that, then I'm thinking that these 3 carbons are these 3 carbons. And so I'm going to kind of label this as green star. I think that that was probably turned into an alcohol over here. So I'm imagining now this being some sort of electrophile that's attacked. Because remember, when we attack a ketone electrophile, it's turned into an alcohol. And then I didn't start off with my carbons. So 1, 2, 3, 4, 5 carbon chunk over here. 1, 2, 3 carbon chunk over here. This is 1, 2, 3, 4, 5 carbon. So we need a different 3 carbon chunk. Okay. Well, I feel pretty confident in these carbons because, like, this methyl, I think is probably this methyl connected to a carbon that has an O, so this kind of carbonyl carbon. So now let's see, where could this be over here? Well, I'm thinking if we have to cut off 3 carbons, generally speaking, I'm like, we're in some sort of electron sink land. I don't see an aldol. This right here is an alpha hydroxy to a ketone, so we're probably not going to do a retroaldol reaction. And so with this, I'm thinking about what are our install sites. We only have a ketone present. We don't have any amines. So I'm pretty sure that this is going to be a TPP mechanism. And here, if we cut...
Wait, Colton?
Yeah.
Sorry. Do you mind repeating why this can't be an aldol?
Yeah. This functional group right here is not an aldol. Aldols are only when we have an OH beta. Exactly. So
okay, yeah. Okay.
If this OH was over here, it would be a different story. Yeah. Okay. So I'm thinking it's TPP, and if we cut here, we make a 3 carbon chunk, right? So I'm thinking that this right here is our TPP install site. And then if this thing is leaving, this is going to be probably a side chain cleavage. Because remember, typically TPP fall into 3 different categories. We're either removing a hydrogen that's next door, we're removing a CO2 that's next door, or we're removing some larger chemical group, some leaving group of carbons that we call a side chain cleavage. And actually, if we have an alcohol at that point, that's the perfect side chain cleavage for us to do a little move like base comes in, removes this, this pushes down, forms the carbonyl, and then we push electrons into our electron sink. So I think this is going to be our leaving group. And then this over here is the electrophile that we attack once we load our electron sink up. So in terms of just answering the question, what's our 3 carbon chunk? Well, it's those 3 carbons, and then this became a carbonyl. We have an H on there, so this is an aldehyde. Cool. So in terms of steps, we'd TPP, make our ILID. We would install our ILID here. Then we would do our sidechain cleavage, load up the electron sink. This would be free. Then our loaded electron sink would go and would attack this electrophile, a carbonyl. And that would make this carbon-carbon bond. Cool. So I'll maybe also label that this blue star is this blue star carbonyl. Okay. And this next one. Oof, there's a lot going on. Let's start with carbons again, because this, I feel like it can easily get stressed and overwhelmed. 2, 3, 4, 5. 5 carbons, 1, 2 carbons. 1, 2, 3, 4, 5 carbons. Interesting. So this has to be 2 carbons. So let me look at my 5 carbon things. Hey, these look pretty darn similar. There's only really one difference in them, right? This carbonyl has become an amine. And when we are swapping a carbonyl and amine, our reaction that we are doing is a transamination reaction. This is the one that has the PMP intermediate inside. And it's going to be the swapping amine and carbonyl. So given that, our other product over here needs to be this 2 carbon chunk, but we swap out our amine with a carbonyl. So I'll do that as this. And again, it's going to be an aldehyde using one of the hydrogens that are on here already. Cool. So our cofactor for this is PLP. And PLP will initially install at the nitrogen, because that's what it's scanning for. So this is our PLP install site. We will then remove this nitrogen onto PMP, and water will come and do amine hydrolysis and install the oxygen there. We'll get out this product. Then PMP is going to take the nitrogen over to this cofactor and install it. As just a rough game plan. And last one here. So already I am seeing fewer carbons in the product. I see a 3 carbon product. And 1, 2, 3, 4, 5, 6 carbons in the start. So with this, what compound functional group do we have? We're always checking for it for this exam. We have an aldol. So this is an aldol, and are we cutting between the alpha beta position? Well, that would make this be a really compelling choice for this 3 carbon chunk. And for our other 3 carbon chunk, we would have these 3. So we have 3 carbons, and that alcohol is going to go up 1 oxidation level to a carbonyl, which again, hidden aldehyde. Lots of hidden aldehydes. So this is our other cofactor, and we are going, or our other product, sorry. And we are not going to need a cofactor for this, because here we are just doing a retroaldol. So we're only cutting. That means that we are doing an aldolase, like step 4 of glycolysis. So we need a lysine residue. So you are going to have a page on the exam that's only doing this, and it's probably going to show up somewhere else too, where you're doing this analysis of the cofactors. Because again, we don't want you to just interpret, we don't want you to just robot write a mechanism. We want you to think, okay, how is nature accomplishing this? You know, like what are these cofactors as tools that can be employed to accomplish certain chemical goals? And so what these pages look like on the practice exams are like this. So it'll give a big long sequence and be like, okay, these steps have which of these cofactors in them. And I think there was a page like this on each one of the practice exams. So if I had to bet money, there would be a page that looks like this on the actual exam. Okay. So with that, any questions on this before we jump into some mechanisms? Cool. Okay. So let's look at this. Provide a complete curved mechanism for the following transformation. Include all catalytic components of the enzyme active site. Clearly show the formation of any co-products you may use, or any co-products, and then you may use any mechanistic abbreviations presented in lecture except for the carbonyl reaction abbreviation shown in lecture 9. So this is going to be some standard language that you might find on the exam. What is this referring to? This is the merry-go-round. This we use with those thiolate reactions. So if we had like a carbonyl in here, we said that we could do this abbreviation here where a nucleophile could attack, we push up, we push down, and then we kick off the thiolate. And we like abbreviated all of that at once to be like, you'll have done a lot of acyl transfers, we'll give you a break there. This can only be used in an FAS question. So this question is not an FAS question, so we can't use that abbreviation. That's all it's saying. Now, with this, we need to be on the lookout for anything in the enzyme active site and any co-products. So let's start our analysis again by numbering carbons. 1, 2, 3, 4, 5 carbons over here. 1, 2, 3, 4 carbons. 1, 2, 3, 4, 5, 6, 7 carbons. So we have 9 carbons on the left, 7 on the right, so we need to have a 2 carbon chunk as well. Now, transaldolase. So this one, we are going to do a retroaldol followed by an aldol. So let's look for our aldol functional group. And we only have one OH, so that makes it a little bit nice. We know that this is our aldol, and so we're going to cut alpha beta to it. So this is a 2 carbon chunk that we're cutting off, so I think that that's going to be the co-product there, where we turn our alcohol into a carbonyl. Yet again, an aldehyde. Okay, so walking through the kind of logic of this. If we are doing this retroaldol, we need to use our lysine to form an imine, and that's going to get us kind of set up. Then 2, we're going to do the retroaldol. 3, because this is a transaldolase, once we've done our retroaldol, we'll be kicking off a nucleophile, and we're going to have to do a forward aldol reaction. So maybe to help us out with that, we know that this carbon over here, I'm going to call it blue star. Blue star is going to be a nucleophilic carbon. We also have, just trying to map some carbons here, this carboxylate, probably going to be the carboxylate over here. And so I think if we have, after that, a carbonyl, and then blue star, this is going to be our nucleophilic carbon. And the other carbons must belong to the other chunk. So with this, I'm thinking that this little ethyl is over here, and then that is our electrophilic carbon. So I will do it as green star. So once we go and kick this off, this is going to be a nucleophile that's going to attack this electrophile in a forward aldol reaction. The last thing that we are going to do is do our iminium hydrolysis. And how did I come up with this? Like this is just the general plan anytime you do a transaldolase. The first half, like if you do not have the aldol reaction, this is a normal aldolase, like the step 4 of glycolysis. And then if you are attacking something new, you're going to insert an aldol reaction in the middle here. So now that we have our kind of carbons mapped out, we know what is happening, let's do the mechanism. So we will start off with a lysine in the enzyme active site. 1, 2, 3, 4 carbons and NH3. And we are going to have our starting molecule where we have our aldol. So, to get us started, we are going to have a base go and deprotonate. Then the lysine is going to go and attack a carbonyl. We are going to push up, and then a lone pair in the oxygen is going to grab a hydrogen from a general acid. So this was form the imine. Now, remember, we do have the mechanistic abbreviation for this anytime we are forming an imine, that we can just write iminium formation. And what's going to be coming off of it is a water, because we want this O to leave as we are forming an iminium, and it's going to leave as a water. So what that's going to turn into is same molecule, but now our lysine is attached. Okay, so now we are, I was going to say now we are lysinated, but I don't think that that's an adjective. Now we are with lysine. So we are going to do the retroaldol reaction. So in the retroaldol reaction, we go over to our alcohol. And a general base is going to come along. General base is going to deprotonate. We are going to push down, form a carbonyl. Then we are going to be breaking our alpha-beta bond and pushing the electrons towards the iminium. So this is our big retroaldol step. When we do that, we get a 2-carbon chunk that now is an aldehyde. So this was broken off from over here. And then the other thing that we get is an enamine. So we still have a double bond here going up to the nitrogen. 1, 2, 3, 4 lysine. So now, again, we used an imine here as an electron sink. Anytime we have electron sinks, if we load up the electron sink with electrons, like an enamine here, then it can go and attack something. For a typical aldolase reaction, what we would do is push down and we would grab a hydrogen. But for a transaldolase, we are going to be attacking a new electrophile. So that's where I'm going to bring in this second molecule over here. So we formed our imine, then we did our retroaldol. Now it's time to do our aldol. So we are going to push down from our enamine, and our enamine is going to go down and attack this carbonyl. It will push up, and then we will grab a proton. And actually, I'll do that as HA, some acid. So we get rid of the particle charge on the lysine after the aldol. Yeah, when we push up to it, we don't protonate in that step because we want it to be an enamine that we're going to push down. Like, you could hypothetically protonate it, and then over here you would have it as this plus, and then a base comes along. but it's fine to leave it as an enamine. As long as you're consistent to show what's happening with the hydrogens, then you should be fine. But I think it's a little unnecessary here. Okay, and then I'll also draw on the lone pair because, again, with exams, we can get a little anal retentive with our lone pairs and our arrows and such. Okay, so now this goes along, and let's see what we've done. So we have our starting molecule over here. We now have double bond again to the lysine. 1, 2, 3, 4. Lyse. We back and restored that. I'm again going to call this my blue star carbon, and that's right here. And then I'm going to call the carbon that we attached green star. So that green star is going to be right here. And then that's going to have an OH on it. Then one away from that, we will have a carbonyl, and then we will have an ethyl. So to look at it, we know that this is a stereocenter we just created, so let's just look at the product and see what that stereocenter is. Oh shoot, I've done something rotten. I have it flipped from how it is in the answer choice. So you can just go ahead and draw it looking like this. Because I've already drawn this, I'm just going to flip the stereochemistry. So if I pancake flip the whole thing over, instead of being on a wedge, this is going to be on a dash up here. But you are 100% welcome to draw it looking exactly like this. And the only thing is you would have double bond down, and then you would have your lysine on here. And honestly, I think that that's the one that's easier. And that's the one that I think will be easier to follow. But because I've already written it here we are. So now we do our last step. Our step 4 is amine hydrolysis. So we need to get rid of our lysine. And so we need a water to come in. So we're going to deprotonate it. The water is going to attack. And then we are going to push up. And again, you can push up and grab an H or just push up to the N. But because we are using an abbreviation here, we are going to do our amine hydrolysis. Then what we are going to wind up with is our product, which again, I'll just draw it the way I've been drawing it. And we are going to kick off our lysine. 1, 2, 3, 4, boom. Cool. Do we need to do the reversible arrows for it? I think you can just do a forward-facing arrow. Like, I don't think that they are picky about it. Just did it. I honestly don't know why I did it. So I think in the abbreviation in class, they just did a single arrow. And in the answer key that I have up, they just did a single arrow. Is it wrong to consider the stereochem at the end when we draw the product? No, it's just also like, we can't predict the stereochemistry. That stereochemistry has to have been given to you. If it was not given to you, then the best that we could do is do a squiggle. Because remember, the only thing that's selecting for that is the enzyme active site. So unless we give you like a pi mole or we give you a final product structure that has it, then it's just kind of a shot in the dark.
I have a kind of weird question that's not like super related to just like this overall question. But if a question doesn't explicitly say we can use acids and bases as needed, are we not allowed to do that, or can we? Because like in the prompt here it didn't say that, but obviously we did that, so I just...
Yes.
Okay.
You always, for this class, can use general acids and bases as needed. Like, we've just gotten to the point where there's literally no mechanism that y'all can do without general acids or bases, unless we give you an active pi mole site where we want you to take the, like, amino acid residue specifically and use that as an acid or base. But, like, everything we're going to do, we're supplying acid and bases. So that does not need to be said explicitly, just because it's in all of them, you know? I think that was something that was more ambiguous in some of the earlier exams when we were giving you more structures of active site residues for something like a protease active site. And in those cases, we are wanting you to use this specific amino acids. But if it doesn't say anything, you can use general.
All right, awesome. Thank you.
Yeah, totally. Cool. Okay. Also, when do we start with lysine RAD protonated? Like, in which mechanisms? I could be wrong, but I think I mostly start with lysine already, like, always protonated. You can start off for a PLP mechanism with the lysine loaded onto PLP, and maybe that's what you're thinking. And then the other kind of, like, where do we start with the protonation states is for FAS, for thiolates, you can start with a thiolate negatively charged. But those are kind of the abbreviations that are coming to mind related to that. Okay, let's look at the next one. So now we are at a new type of enzyme called a transketolase. Now, I don't know that we did many transketolases explicitly. You did do some of these reactions. I just don't remember if we called them a transketolase. So, transketolases normally use one specific cofactor, but because we don't know how familiar this term is, or I don't remember how familiar this term is for y'all, let's analyze it and see if we can come up with what cofactor we should use. So it's the same notes here as before. Of you just can't use the merry-go-round. But let's see. You start off with 1, 2, 3, 4 carbons. And 1, 2, 3, 4. And we wind up with 1, 2, 3, 4, 5, 6 carbons. And 2 carbons. So all of our carbons are accounted for. We have all of our products. We're doing some sort of cutting. And so one thing I might scan for is, do we have an aldol? And over here, we have alpha beta. So we do have an alpha beta aldol over here. But if we cut there, that's cutting off a 1 carbon chunk. So that's not what we want over here. We're going to have a 2 carbon chunk. So we are not going to do an aldol there. And then over here, we also have an aldol reaction. And if we cut here, we do get a 2 carbon chunk. However, I'm not certain that that is actually going to be helpful for us, because here, the 2 carbon chunk that we would get off, that is going to just be, like, there wouldn't be an OH here. And so I'm not sure about that. So that's one that we can consider. But maybe let's try to start mapping carbon. So we tried out looking at these aldols. And again, this one still could be true. We haven't fully ruled it out. We've ruled out this one. But let's start off by being like, what's the most prominent structural feature? It's our phosphate group, right? And then with our phosphate group, let's look at this. We had skip a carbon and OH, skip a carbon and OH. And then we had skip a carbon carbonyl, skip a carbon. This could have been the side of a carbonyl, maybe. So I'm going to venture a guess. We don't know if it's for sure, but I'm going to guess, what if that carbon is this carbon? Because that would make sense that we have an OH where a carbonyl was, and our kind of boring carbons of our sp3 carbons, like alkane carbons, are where we expect them to be. So if we do that, then where did these other ones come from? Okay, well, over here, this, to me, looking at this, looks most like this carbonyl and this OH. So my current hypothesis is, what if we cut here? So I'm going to call this a green star, and then we have the OH over here. And then could this 2 carbon chunk line up over here? Well, if we cut at this point, what if we make this our carbonyl, and then we have a CH2OH, CH2OH. That seems like it could line up pretty well for me. Do you all buy it? in terms of this mapping of phosphate group onto each other. From there, counting down and seeing which carbons have interesting things on them. This one kind of lines up over here. And then being like, okay, well then where did these two come over here? Probably this end. Any objections? Any other ones that you're like, how could we rule this out? I'm gonna delete these aldol circles just because that didn't end up being helpful. Again, it's good to check for aldols, but we're not always going to be doing it. Okay. So now, with this, if this is where we're cutting, we are cutting between the alpha position and a carbonyl, so what cofactor should we use? Well, TPP, because TPP is the one that's going to be scanning for carbonyls and then cutting adjacent to them. So if we think about this, TPP, this is going to be our install site. This is going to be our leaving group. And then this is going to be our electrophile for our TPP steps. We're going to attack over here at this carbonyl, and when we attack carbonyl, it's turned into an alcohol. So let's see if we can list out the TPP steps just from like what we remember of TPP reactions. So TPP, we have step 0, which is make ylid. We have step 1, install TPP. Step 2, we load electron sink and leaving group leaves. Step 3 is the electron sink loaded nucleophile. Attacks some electrophile. And then we uninstall TPP. These are just like framework. Anytime we're doing a TPP reactions, put it on, load the sink, attack some electrophile, take it off. So, again, the more that we have our kind of like framework memorized, the easier it's going to make working through the actual mechanisms. Having the framework down and then analyzing the carbons at the top, I think, is going to be your biggest key to success here. So, I will start off by making the ylid. Is that the right TPP structure? Well, I'm missing a plus, but yes. So some base is going to come along and it's going to deprotonate it, making it ylid. And yeah, I'm going to try, I'll see if I can keep up this color coding. I'm going to try to make TPP purple, because that's what I did in all of the section stuff. So now we need to install our TPP. So this was our step 0. And I'm going to get our molecule where TPP is going to install. And TPP is going to go and attack the base of the carbonyl, push up, and we are going to protonate the carbonyl. Now with how I've started this, I feel like it's going to do a weird snake. Give me 1 minute. So maybe I'm just going to just take it down and we'll see if we can get that sorted. So, and actually I started off drawing this like it is in the starting material, but instead I really want to draw it to highlight the TPP. So I'm going to copy and paste my TPP structure. And what is leaving? Well, the bond I want to break is this bond. So I want to make sure that that bond is looking in the right way for our MO diagram explanation. So I want this bond that I'm breaking here to be perpendicular up like this. And we are going to have an OH off of it, and we are going to have this OH here, which part of me is like, I want to double check the stereochemistry of this. I know I need to add a dash or a wedge here, but we have that going on. Then we are also going to have an OH, and we are going to have a carbon and an OH down here. So with this, I think it's the one where like technically we should keep the stereocenter the same because we're not really doing anything with this. So it should look exactly the same. And so I might just really really quick check R and S. So this is priority 1, this is priority 2, and priority 3. 1, 2, 3 counterclockwise, so it's S, and our 4th priority hydrogen is going away. So I need to make sure whatever this is, it is S. So I'm going to try it on a wedge. So this would be priority 1. We said this, that was the carbonyl, was priority 2, priority 3. If we 1, 2, 3 like this, it's R. So actually that needs to be on a dash now. And again, you can draw it in whichever way you want as long as you draw the correct stereocenter. So if you want to draw it looking more like this starting material, go with God. If you have to draw out the MO requirement, then they're going to want you to draw it in the correct orientation like this so you can see it perpendicular. And so I'm drawing it here in case you were asked the MO question, what is the MO requirement? You need the bond that's leaving, the sigma CC here, boop, to overlap with the pi star CN. So that's pi, and we need to make it anti-bonding over here, so we shade in 1/2 of each. And again, we want to make sure that these can flow easily from the sigma CC to the pi star CN. Now, with this, you might have seen in some of the answer keys that you can also say it's perpendicular to the entire pi system. That is fine and dandy, and that will earn you full points if you do that. I don't like that as much for my personal taste as like a chemist, because when you talk about the pi system and you draw them all like this, where they're all like shaded the same way, this is not showing an acceptor orbital. It's showing like a filled orbital. And again, I like thinking about filled orbitals donating into unfilled orbitals, a pi star. So again, it's a preference. We will take credit for either of them if you draw this pi star CN or if you draw the entire pi system. But just wanted to flag that as like different people have different preferences for that. So now we are going to do our loading the electron sink. So I'm going to draw out this hydrogen. I'm going to enlist the help of a general base. The base is going to remove a hydrogen on the OH. We push down, make a carbonyl. Then we break this carbon-carbon bond, push electrons down and into our TPP. So with that, first off, we kick off this aldehyde with an OH, and hey, that's one of our products. Also noting that this was step 1, this was step 1, install TPP, and then 2, load up TPP. And now, when we do that, what we are getting is we have our OH here, we have our OH down here, and then we have our TPP, bond, methyl, bond. But now this has a lone pair, and we have a little enamine nucleophile that can go and attack something. So at this point, we bring in the other molecule that we have. So I'm going to bring in O3PO2 minus an OH. So now we do step 3, which is our nucleophile that we have. Our enamine nucleophile is going to go and attack some electrophile, which is the carbonyl on the end. We are also going to have the help of general acid. So now, with this, I don't want to deal with stereochemistry and drawing it weird ways. So to be so honest, what I'm going to do is I'm going to look at what the product looks like, and I'm going to draw it really similar to that. So I'm going to draw 2 minus O3PO 1 We have this OH, we have this OH, we have a carbonyl OH. I know that this is where I'm headed for my product. We're not there yet. We need to be one step away from it though. So we need to have this, but we still are going to have, oh, I deleted a carbon, sorry. We have one carbon and then an OH. So I still need to have the TPP installed. So the TPP is going to be installed here. So let me erase this, and at this carbon is the one that's going to be the base of the carbonyl, so that's going to be this carbon over here. So we have this branch to OH, that's going to be on there. We need to have another OH, and we need to have our TPP on here. And so, the only thing that we can do at this point is get off of our TPP. So this is our step 4 here. With this, we just need to reform our carbonyl. So we're going to enlist the help of a general base, reform our carbonyl, kick off our TPP ylid. So, and remember, we do not have to redraw the protonation of our TPP. We can leave it in its ylid form. And there we have it. So, again, it followed the plan pretty closely here. In the next couple mechanisms that we're going to look at, things are going to get a little weirder. Any questions on this one with the TPP mechanism? Also, looking at the time, these problems, these mechanisms are probably going to take the full time, so we probably won't go through a practice exam. But I'll be around for another 2 hours after this, so feel free to hang out in office hours and we can work some of those problems. Cool. Okay, next up, we are told we have a PLP in the house. Dun, 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 dun. And who? This is weird and funky. So, automatically, I'm seeing this thing over here and being like, that looks kind of like this. Do you buy that? It's like an oxidation level 3, 2 boron carbons, oxidation level 3. I think that we must be cutting there, and that this thing all the way up here is this thing all the way up here. And the thing that is concerning about that is not immediately next door to a carbonyl or to a nitrogen, right? And specifically, PLP we know installs at nitrogen. So we can install a PLP here, or we can install a PLP here. And typically, we're thinking about cutting right next to it. So something else must be happening. Okay. Let's look at this bad boy. So we have our sulfur, and then we have all of this. Well, that's probably over here. So we've kicked this off, and then we've added this sulfur over here to this position. So I'm going to make this a blue star over here because that seems like an interesting position that we are working with. And that's going to be this blue star over here in the product. And I don't know exactly if we have used this terminology yet, but let me kind of introduce you to some terminology. If we look at this, for our amine, this is the alpha position for the amine. This is the beta position, and this is the gamma position. And anytime we have interesting stuff happening at the gamma position, if we have a leaving group, gamma to an amine, this is going to be our E1CB tip-off. So our E1CB mechanism, I'll go briefly back to the section notes, looked something like this. So we were looking at the DCC inhibitor DFMO, or I said DCC, ODC, sorry, ornithine decarboxylase inhibitor. And DFMO had these fluorines on it, and what happened was PLP installed its nitrogen, and then once it got installed, sorry, this is the like overall reaction and this is the mechanism. Once the PLP got installed at the nitrogen with the transil lamination, we loaded up our PLP, and then the PLP did this kind of super lone pair push thing and kicked off a fluorine. And this is what we mean by the E1CB mechanism here. So it means that we are going to be forming something that's kind of like enone-like, where we have an extra double bond created. I'm trying to think of another example of it. So this one, I think, is the classic framework that you use if you're kicking off a halide. We're going to be kicking off something a little weird. But one thing to notice here, this alpha, beta, our fluorine is going to be gamma to the nitrogen that we kick off here. And so we're seeing that pattern of it's a little bit further away from our nitrogen. It's not just right next door of something that we are cleaving. Like a decarboxylation, it would have to be right next door to the nitrogen. But again, this is a very kind of specific example of it. Let's go back and look at how this might be connected a little bit more. So first off, we need to connect this sulfur to that gamma carbon over here. And we know that this sulfur is likely going to be a nucleophile of some sort. Sulfur goes and attacks other things. So if we need a carbon electrophile that's a little bit away from our amine, what we are going to try to do is some sort of like, what is the word for it? I want to call it a Michael reaction, which again, it might be a minute since you've heard of the Michael reaction. A Michael reaction is when you have a nucleophile or like an enolate attacking 1,4 to an enone. And so it's going to push up like this. So this is kind of the general idea. And I know that this is a little like wishy-washy confusing. It might be one where we have to look at it a little bit once we are already under the hood of the mechanism. This might not be one where we can figure it all out by just analyzing the starting materials here. But let's try to get into it and see what we can do to try to get something that looks a little bit like an enone, to try to get something that we can push off this leaving group E1CB-like. Maybe the last thing I'll say with the E1CB mechanism is E1CB happens in the typical aldol reaction. And it's when we go from our aldol to our enone product. So the way that this happens is you deprotonate at the alpha position to the carbonyl. That is going to go over here and make this now an OH. And then you're going to do this push from the enol over and then kick off the OH. And that forms your enone. So with this, the whole idea of an E1CB addition is you are deprotonating and loading something up with electrons and then doing a big push and kicking off some leaving group. So here was our leaving group. So with this in mind, let's try to jump into the mechanism and see what's happening. So let's start off with PLP. And what color did I make PLP in the section notes? I think I kept it purple, just like TPP. So we're going to start off with a loaded PLP. So it's going to have our pyridinium ring. And we'll do NH lyse enzyme, the plus here. And we're going to start off with our transaldemination. Now we could attack at either of these, but because I see the leaving group is attached to this molecule, then I want to install PLP closer to that molecule. So we are going to install PLP here. This is going to be our leaving group. This is going to be a nucleophile that comes in. So H3N O minus and I'm actually going to write this as NH2 and one more H. Then we're going to have 1, 2, and then we'll have O, 1, 2, ba, O, ba. I'm making it very small because we're going to have to write it several times. So we deprotonate. This goes in and attaches at the aldehydic carbon, and then we push up. And this, we can write our transaldemination. And then the thing that's going to be popping off out of it is H3N lyse enzyme. So now, from here, we have our PLP. And we have all of this nonsense. So, once we have our PLP loaded over here, the question becomes, what bond do we break to load up our PLP with electrons? We have 3 options for the bonds next door. We can break off this CO2 and do decarboxylation, but that CO2 is still in there on the product, so that doesn't work. We could break this carbon-carbon bond, But then that's going to break off this whole chunk. It's going to break off this as well as 2 other carbons. And that's not there in the product. Like, those carbons are still on here. And so the only other thing that we could remove is the hydrogen. And the hydrogen's kind of unassuming because that hydrogen, or a hydrogen, is still there in the product. But because cutting off these don't make sense, the only thing that we can cut off is the hydrogen. So what we're going to do is we are going to get a general base to come in. And we are going to load up our PLP. So now we are at a quinoid intermediate. Here. Okay, so we are at our quinoid. Our next goal is to figure out how to get this thing to leave. So somehow we want to do something that can make a double bond here and get this to leave that's kind of E1CB like. Now, if we were doing straight up DFMO, DFMO would be pushing down, over, 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 but then that would kick off this whole entire thing. That's not the right placement for where we are going to do our lone pair push. So instead, what we need to do is we need to think about treating this like an aldol. So imagine this was like an OH here, and we have a carbonyl here now. This is an alpha beta hydroxy. And the way that we did our E1CB mechanism for the aldol reaction is we deprotonated here to make this into a little like enolate, and then we pushed all the way over. We did our E1CB step. The thing that's a little tricky with this is we have this loaded up quinoid, and the quinoid is going to want to attack something. So what we're going to do is we're going to release the electrons of this quinoid intermediate and let it go and attack something, but we are going to do that step where we kind of sever this PLP ring from the rest of it by just protonating at this site, at the aldehydic carbon. So let's see what that looks like. So now we've restored our aromaticity down here with our PLP, which we know is a big driving force, making an aromatic ring. And now, homegirl over here is just a plain Jane aminium. So let's try treating this carbonyl that has alpha beta to it, a leaving group. Let's try treating it like we would an aldol reaction. So we're going to take one of our hydrogens, our alpha hydrogens next door that we know are acidic, and a base is going to come along and deprotonate it. We're going to deprotonate, push towards the nitrogen. When we do that, let's see what we make. So we've now, when we deprotonate the alpha position, made an enamine here. And this enamine is ready for our E1CB doing that super lone pair push. So we are going to push down, over, and kick off the leaving group. So this was our E1CB step. And again, E1CB It's E1 because we're going to be making an alkene over here, elimination. And CB because it was formed from a conjugate base, from deprotonating at the alpha position here to the iminium. So now, when we do this, we've reformed that, but we've made this thing that looks kind of like an enone. It's with a nitrogen instead of an oxygen here. And then the other thing that we've done is we've kicked off this whole side group. So that is done. It is kicked off. And now, looking back at this, we said that this carbon over here, blue star, that was 2 away from the nitrogen, that was going to be an interesting point. So this blue star here, it is the one that had the leaving group that just left. And now, because it is in this enone-like structure, that is an electrophilic site. So a nucleophile can come in and attack this 1,4 and push all the way up to the nitrogen. Cool. So let's do that. So this is our electrophilic site. And here we're going to bring in our other molecule. So our other molecule was... Oh wow, I've expanded. I've gone way over here. Let me move this around a little bit just to kind of fit it all on the page. I'm going to go ahead and move this all the way over here, and we are just going to do this straight across. This was our U1CB step. We are kicking off this as a product. And we are at this intermediate. Cool. So at this point, we are going to bring in our cysteine. And with the help of a general base, we're going to be deprotonating here, and then we're going to have our thiolate attack 1,4 on this system. So now, when we do this, we have still this cutoff ring that's still disconnected from everything. We're going to have to deal with that eventually. We're going to have our NH here. We have our carboxylate still down there. We have our star carbon up here. We've moved the double bond down here. And on that star carbon, we need to have that whole thiolate moment. So I'm going to draw it like the product up here. So that'll flip the stereochemistry around to dashes. So we'll have the S. And then we will have the H3N and the carboxylate. So woof. a lot's going on. It still feels like we are in the dark. We don't have our full exit strategy yet, but we've accomplished our two kind of biggest goals. So we had to get this thing to leave, and then we had to get the sulfur thing attached. We have done those. So now at this point, we just need to kind of pick up the pieces and get our PLP out of there. We need to close up the patient and leave. So once we have done this, we are at... Oh, I've made a small mistake. I think I added an extra carbon. So mapping these onto this, we had carbon 1, 2, 3. I've added an extra bonus carbon. It happens to the best of us, and it's honestly one of the most likely mistakes that is made on an exam, is just adding a bonus carbon where there should not be one. So we should have 1, 2, 3, and goes directly up here. So that means our double bond's here. And that's more normal because we should have an enamine after this. Like we attacked 1,4, so we're making this double bond right here by the nitrogen, an enamine. And so now, in order to get this PLP off, what we need to do is we need to do a tautomerization from our enamine back to an imine. So we're going to use a general acid here and get this back to an imine. Okay, we are very close. Now we have reformed our imine. All we need to do is we need to reconnect our PLP and then get it out of here with a transaldemination. So what we need to do is to reconnect our PLP, we have to deprotonate here. Down, over, down. I'm just going to copy and paste all of this nonsense. Okay, so now we are at our quinoid intermediate here. And we need to reform our aromatic ring, but we need to do so in a way now that this whole thing is attached. So what we are going to do is we are going to push all the way out, and then we are going to protonate at this position. Because we know that we need to get the double bond in this position in order to do our transaldemination and bringing in the lysine and kicking off PLP. So with this, we now have made it so that the double bond with the nitrogen is this direction. We have our full aromatic ring again. And now all we need to do as our last step is bring in our lysine with a general base. This to go attack and push up. I'm forgetting some formal charges. So anytime a nitrogen has 4 bonds, there we are. We have a positive formal charge, so we write our transaldemination. And what do we have out of it at the end of the day? Well, this whole thing releases our product. And that's NH3. So we have that product done. And we've kicked off our primed PLP. So, I don't know about y'all, but this question was kind of soul crushing for me. I'm like, woof. That's so much. That is so long. How are we to ever figure this out? So, whenever I get to a hard question like this, where there is a lot going on, the most important thing I can do with this, with studying, is go back through and analyze this answer and try to figure out what happened and what I could have done to have like tipped off future Colton for like, hey, how do you do this? What's going on? So I'm going to go through and I'm going to like summarize each of these steps. And I know it's kind of belabored to spend more time on this, but I do think it will be helpful to be like, okay, how do we approach a monster PLP question like this rather than just kind of let it be thrown to the wind. So let's try it. First step, and I'll do my analysis here in kind of an obnoxious orange. We installed PLP at the nitrogen. Our second step is we did an alpha deprotonation to load the sink. And then 3, we cut off the PLP from everything else going on. And we did this by doing an aldehydic protonation. If we had done a protonation at our alpha carbon, and just to remember nomenclature, we call this one the alpha carbon, and we call this one the aldehydic, because that one was the aldehyde of the original PLP. If we just protonated it over here, we would just be undoing what we did in the first step. So, like, we would just do directly undoing it. So, here, we are protonation at the aldehydic position so that our PLP is just kind of cut off from everything else that happens. It's basically like saying we're going to take a pause break in the middle of a big PLP mechanism in order to do some other chemistry. Okay, so now that we've done this pause break in our PLP mechanism, what did we do? Now, we did a deprotonation here to form an amine. An enamine. So I'm going to say that we did an alpha hydrogen deprotonation, because if we have this as the amine, this is the alpha position to it, to tautomerize to an enamine. And then step 5, we did the E1CB and push off a leaving group. Okay, we pushed off our leaving group. Then what happened? Step 6, I guess it is. We had a thiolate nucleophile attack 1,4 on our kind of enome and push up. Step 7 here is we tautomerize back to the imine. In other words, we did the alpha protonation. We did kind of the opposite of this step. This step we went and formed an enamine from an imine. Now we're going from an enamine back to the imine. Then, step 8, we reconnected the PLP by doing an aldehydic reprotonation, or deprotonation, sorry. Then 9, we did our normal alpha protonation and restore the PLP aromaticity. We got rid of our quinoid. And then our last step here is offload PLP. So pointing out a few things. This step right here, where we cut off PLP for our aldehydic and like separated it, that, where did we reconnect it down here? We reconnected it down here at 8. So everything else in the middle was stuff that happened in between. And this was our E1CB mechanism steps. So the big kind of goals that we're trying to do. This was the thing that was new and weird in this reaction. We had to get a leaving group to leave down here. And so we had to do our setup for E1CB and then the push off. And then this created an electrophile for our nucleophile who go in and attack. And this is the kind of consequence of that conjugate addition. So the new stuff in the middle. And then we had to do our kind of closing steps. I would be shocked if you had a mechanism this long on the exam. I would be shocked. Like a 10 step mechanism, this is probably harder than what you were going to see. What we might do is like we might choose to start at one point in this. Like everything in this I think could be fair game. It would not be fair game to ask you all of it. So we might be like start at this intermediate and then do this. Or we might say something like give you a intermediate goal to get to. We might just say go to this point or something. Or we give you this as the ending product. But this is brutal. I would not be super worried about it. Again, you should be at the level where you are understanding this chemistry, but coming up with it on your own is the hard part that you should still be in the process of putting together right now. Again, because this question feels rude, any other questions on it before I move on? Because I feel like I've traumatized all 14 of you in the Zoom room and unknown future students watching the video. In the original version of the notes, there was like an extra page after this. And I was like, I don't need an extra page. Why do we have that there? Now I see why we need the extra page. Okay, let's do this one last one, this FAS concepts. This extra practice cofactors one, all it is a transamination mechanism. So this one's good practice. This has PMP in it, but we're probably not going to do it here together. So again, I think it would be good practice, but it's a pretty straightforward PMP like transamination. So looking at this with FAS stuff, a certain microorganism was found to only express a variant of FAS that catalyzes the transformation below. Importantly, only KS and ACP domains are involved. Okay, so that's the like Claisen steps of FAS. And the product is liberated from the enzyme via a sequence of 2 spontaneous transformations. Very interesting. Provide a complete curved mechanism. Be sure the starting materials are bound to the correct domains, so SR. So basically what this means is this S, we either need to connect it to our KS domain or we need to connect it to an ACP domain. So we have to figure out what those R's are here. And we can use any mechanistic abbreviation. So we can use our merry-go-round. Woo! Okay. So let's try to start mapping materials onto the products. So spontaneous transformations Hmm. Well, we at least have this R that we can kind of latch onto. So this is probably this, right? Okay. The other thing that I'm seeing is this carbon over here is at oxidation level 3. So to me, that's telling me this is either going to be this one that's at oxidation level 3, or it's this one that's at oxidation level 3. Because of just literal proximity of where it is, I'm going to take a stab in the dark and say this is that. Well, we'll see. We'll have to like map other things and see if that kind of locks in together. But let's go right now with the assumption that these are these. Then the rest of this has to come from the other molecule, right? Well, the other molecule, one of the things I'm seeing are these diols, right? Like these two O's. And I see a few O's here. But in terms of being right next to each other on adjacent carbons, the only ones, I guess we could do this, or we could do this. But this seems less complicated, so I'm willing to bet that's this end. This carbon was a oxidation level 3, and now it's being turned into an enol. And so I think that because of oxidation levels, this is going to be closer to this side. So let me try to imagine these as those like diols. So we did some sort of connection here to make an ester. And then on the other side, that means that this carbon that was the thiolate is this carbon. So somehow we need to connect this carbon to this yellow carbon up here, which I'll do with a green star, in this starting material. Another thing I'm seeing with this is, technically, this is an enone. So I'm thinking about an aldol reaction. Other things, where did she go? I feel like she got cut off. And if she got cut off, we would have what else over here as a product? CO2 gas. I'm not going to do the process of counting carbons, but there is a carbon missing, and this is the carbon. So we can double check with that. The other reason that I'm thinking that this leaves is, remember in the normal FAS reaction, when you have the KS and ACP domain, you're doing a decarboxylate of Claisen. So I'm thinking that this is going to be the thing that decarboxylates and makes our nucleophile, which would make this one the electrophile. So we have our decarbox Claisen. So this is going to be our nucleophile, and then this is going to be our electrophile. So which domains are associated with which in FAS? So our nucleophile is always going to be the incoming thing that's going to be on our ACP. And then our electrophile is always going to be on our KS domain. We've loaded it, ready to do the Claisen. So let's go ahead and draw these with the domains. Okay, and then this one over here. Wow, I'm drawing with black for the first time, and I'm like, wow, how morose. Again, I think it's because I've killed the vibe and spirit with the last question, which I didn't even write. This question, it was really rude. Yikes. Okay, so we start off by doing our decarboxylation and loading up our enolate ready to attack. So CO2 comes off. And then over here, this is now going to be an enolate. And remember, we can leave it as O-, not protonate, because it's a thiolate enolate. It's from this thioester. Now, we are going to bring in our KS domain, and we're going to have this attack. So with this, we get to do our loop-de-loop. So we push down, this come over and attacks, we push up, then we push back down, and then we kick off our thioester, or our sulfur, I should say. So with this, let me try to draw this in a way that's more natural for the product. So we've reformed our carbonyl here, and then I called this carbon green star initially, so let me label that green star. And then this carbon over here was blue star. So let me add the blue star over here. So blue star was what was attacked by green star. And then we are going to have a carbonyl on her. And then we are going to have OH, OH. Okay, same. So this was our kind of FAS step, and now we need to figure out what other kind of spontaneous steps are going to get us here. So one of them that I'm seeing is we need to make an ester, and this is a thioester, right? And so normally with FAS, if you were to try to like get this free, you would have a water come in and you would deprotonate it and it would attack here, and then we would cut this off. But now, since we have something on the molecule that can do this intramolecular reaction, we're going to have this thing come and attack. So we're going to deprotonate this alcohol. This alcohol is going to come attack, push up, push down, kick off the thiolate. And one thing I forgot to write over here was our KS domain thiolate. That was done after that first attack. And now, after this attack, we are forming... The O is down here. We've made our little 5-membered ring. And oh my gosh, I'm so sorry. I used the wrong OH. So we need to do it from this nearer OH, because that's what's going to make the 5-membered ring. So our base is over here. We're going to deprotonate this OH, and then that one's going to attack. And that's going to make a 1, 2, 3, 4, 5 carbons. So there we are. So we still have this far OH dangling off. And then this is going to be our blue star position. This is going to be our green star position. So I need to add some more carbons. Here we have a carbonyl. And then we have our R group. So we have made our ring here. And I am also missing a carbonyl. Ding dong. This carbonyl just got deleted. But we are close to our product now. We've gotten off all of our FAS domains. So our ACP with its pantathionyl arm is off. And now we need to go just from this being a carbonyl here to it being an enol here. So we're just going to do a little keto-enol tautomerization. So for our last step, we are going to deprotonate here. That is an alpha hydrogen, and we can think about this as being really darn acidic, because not only is it alpha to 1 carbonyl, it's alpha to 2 carbonyls, it's alpha to 3 carbonyls. So it's going to have a pK of like even lower than 11. It's going to be quite acidic. So from this, we are going to deprotonate, push down, push up, and then have our oxygen go and grab a hydrogen from a general acid. And then that will take us to our product here. Work. Okay. This has been a lot. We've covered a lot. We've touched on a PLP mechanism, a TPP mechanism, an aldolase mechanism. So we've kind of seen one of the big of each types. But from this point, I think that the biggest thing that's going to help you is working through those practice exams. As always, you can always email us with questions, and we have a bunch of office hours over the next few days. So if any questions come up as you are working, please feel free to stop by or reach out. But with that, thank you for staying. Sorry for going a little bit over, but we survived. We've survived some very hard problems. Good luck with studying this week, and I'm going to take a little break and be back at 8:15 for some practice questions or office hour stuff. Cool. I'll see you then.